Good afternoon, everyone. I am Branavan I am with MillenniumIT of the London Stock Exchange Group. In this talk today about technology trends in capital markets, I am essentially going to touch on a few novel trends, novel directions that we are taking at MillenniumIT. Specifically, two areas. The first is a set of technologies that we like to call description driven systems, and the second is automated systems monitoring. So, let me start with the first one. Now, I am sure everyone here is really very familiar with the software engineering process, the process of engineering enterprise software systems, but just for the sake of the presentation, let me belabor the point. Now, we would start with some business functionality written out in specification documents. Say, we will hand that over to an engineering team, which would go off for a few months or a few years and build that system that we wanted. Now, as we all know, this process is very expensive and very error prone, and also it can be a very uncertain process. Now, heaven forbid if you want to go in the opposite direction, if you wanted to take a system that exists and understand what it does, if you want to go from the system to the specification, it is even harder. So, going from a spec to the system is hard, going from system to spec is even harder. Now, why is this? If you think about it, the business specification is a very high level statement of requirement. So, it's at a level of it's at a very high level of abstraction. The system itself by nature is a very low level detailed implementation. So, there is an abstraction, there is a gap in abstraction between the specification, which is a high level statement, and the implementation, which is a low level statement. And when we build a system, or when we try to understand an existing system, we are spending a lot of human effort trying to cross this abstraction gap. So, we are taking a high level statement of functionality, trying to figure out how to convert that, how to cross this abstraction gap, how to convert that into an implemented system. So, this is hard. Now, what can we do about this abstraction gap? Now, it is not going away, right? It is part of the nature of the problem. But what we can do though is to try to reduce the amount of human effort required to cross that gap. The way we are approaching this problem is by adding a high level formal spec in between the two. So, we still have the high level business spec on top, we still have the detailed system implementation below as is needed, but what we have now is this additional high level formal spec. The important thing is that the difference in abstraction gap between the business spec and the formal spec is small. So, the human effort that goes into converting the business spec into the formal spec is correspondingly small, and also that process now becomes a lot easier to do, it becomes a lot less error prone. To go from the formal spec to the system implementation itself, we use automatic code generation. So, to go from to cross the full abstraction gap, we take a small step using human effort and a second bigger step using automated code generation. Now, this we do using a toolkit, which essentially is a set of domain specific languages. Right. So, in our case targeting the trading and financial domain. These languages, so one of the key features of these languages is that they allow us to specify the system at a very high level of abstraction, which is what gives us the advantage. So, we can define the data, we can define the computation, we can define the workflows, the interfaces, all aspects of the system in one coherent integrated fashion. The specification can be very concise because of its level of abstraction, and this is possible because the toolkit has advanced automated inference built in. So, for example, it can infer details of computations based on the data specification that you are given it. It can infer details of the interfaces, again based on what computations are going to be done on the inputs of that interfaces. The languages are also very strongly typed, which helps in the inference that we need to do. At compile time, so we take the business spec, we convert that into a formal spec, and then we give that formal spec to the toolkit, which goes off, compiles that specification into a runnable system. And during that compilation, the toolkit is capable of verifying the entire specification. It's capable of verifying that your spec is actually coherent, that you have not specified something in one place that does not match with a different part of the specification. So, because this toolkit allows us to reduce the abstraction gap that needs to be crossed using human effort, we are looking at efficiency improvements that are several orders of magnitude. Okay. So, that is the first half of this description driven system story. Now, I am going to be in the interests of time, I am going to be very brief. If you have any questions, please feel to ask at the end or come and talk to me afterwards. The second half of this story is to deal with the definition of the behaviors of asset classes and instruments. So, all of our systems deal with different instruments, different asset classes with often wildly differing functionality. So, let me again go and talk about how we would build this traditionally. So, if you take a traditional system, let us say in this case a post trade system, you would have, the system would handle some set of asset classes, and all systems as they exist now allow for certain amounts of configurability. So, you might be able to configure the behaviors of the asset classes, perhaps using a collection of attributes or perhaps using rules, but in any case a large portion of the functionality of those asset classes would actually be fragmented out into different parts of the system. So, the code of different components in the system would have large portions of the functionality of your asset classes. What this means is, if you wanted to change functionality, if you wanted to add a new asset class, you are going to have to go and touch a large portion of your system's infrastructure. Okay. So, any change leads to change in a large portion of your system. What this means is a whole host of significant disadvantages. So, if you now essentially what we had was locally encoded product behavior. So, the behavior of the asset classes is locally encoded in different parts of the system. This very importantly obscures the functionality of your system. If you take one asset class and ask the question, what does this asset class do? It is very hard to answer that question, because you need to go and look at lots of little pieces of your system. Now, this promotes fragmentation. If you can't understand what your system does today, if you wanted to do a change, that change cannot be holistic. Okay? You most likely will go and say, okay, let me, in the interests of cost and time, make a local change that adds on to your local changes, increases fragmentation. That hinders integration and unification of your systems. Very importantly, this reduces information reliability, because again you are not entirely sure what your system does, increases operational risk, increases cost. So, these are all sort of disadvantages that come from the fact that the functionality of asset classes, which by requirement changes on a very frequent basis, is fragmented out into different parts of your system. Now, imagine an alternate universe, a universe in which your system itself is agnostic of your asset class functionality, and all functionality of asset classes, all behaviors of asset classes are encoded in one central place. So, if you take a single asset class, all of its behavior is in one place. You take that package of asset class behavior definition, put it into your system, and now your system is capable of handling that asset class, all the functionality of that asset class. Now, if you had something like this in this alternate universe, a lot of things would change. You'll have a lot of those disadvantages that we have now would convert into significant advantages. So, you'd have clarity of system functionality. If you wanted to know what does a specific asset class you do, you go and look at its definition and it's all there. You don't need to go off and look at the rest of your system. This promotes integration and coherence of your systems, increases business agility because changing an asset class now becomes significantly more easy, reduces information loss, increases information reliability, all of that reduces operational risk, reduces cost of ownership. So, this idea of going from asset class functionality that is coded locally in different parts of your system to extracting all of that functionality and defining it in one place has major advantages. Now, perhaps this alternate universe can actually be a reality. So, the way in which we are trying to address this is again using a description language, but in this case we are talking about a description language that is actually an algebra over asset classes. So, if we take again post trade as an example, a post trade description language that allows us to define asset class behavior would be an algebra over the set of all post trade asset classes. What does it mean to be an algebra? We have a small set of primitives and operators that cover all the asset class behaviors over all system functions, but importantly any asset class that is part of that algebra, if you take that and apply any other primitives or any other operators, is guaranteed to be another member of that same set of asset classes. So, you can by definition guarantee that any asset class that you define in this language will work on your system, because that is the property of an algebra. Okay. Now, so I am now talking about this an algebra, a mathematical construct. I am saying we want to create a description language that is a mathematical construct that will allow us to define asset classes. That implies we need to have a very precise understanding of the system that we are trying to build. So, if we are trying to build a post trade system, we need to have a very precise understanding of a post trade system. So, we have started off so this description language is built on a mathematical model of a post trade system. So, essentially take the business spec, understand it and convert that into a very precise mathematical construct. Okay. How are we doing for time? Okay, we seem to be good. Now, the second part of my talk is going to be about automated systems monitoring. So, again a slightly alternate imaginary universe, but possibly. Now, take the systems, the enterprise systems that we deal with on possibly a day-to-day basis. All of these systems are extremely complex. We are going to be dealing with tens of servers, hundreds of servers, hundreds of complex network structures, hundreds of processes, hundreds of gateways, hundreds of users, thousands of interfaces, millions of messages. And we have these complex systems and we expect a small number of human operators to ensure that these systems are operating perfectly. How is that even possible? How can you even sit there monitoring thousands of statistics and messages and make sure everything is running perfectly? Now, if something goes wrong, then obviously it will be caught, right. So, the moment you have an error, it is up there staring in your face, the operator will catch it, you do something, but that is reactive. What about all the warning signs, things that might indicate of future errors? Those get missed in the mass of statistics and messages that these human operators have to monitor. Now, if you in the ideal case, what we would like to be to lead to a problem, they can fix it before the problem happens. So, events that can cause future errors, resource usage trends indicating future capacity problems, missing events. So, maybe a few messages sort of disappeared and never got out of marker data system, unusual system behavior indicating underlying problems. So, ideally we would like to somehow filter these out and present them to a human operator, and filter out all of the rest of the normal sort of messages that you would see in a normal operating system. So, what you could imagine doing, and this is what we are trying to do, is to learn is to build an adaptive filtering system, one that would learn the behavior of the system that it is monitoring, and based on that give human operators a very nicely filtered set of messages. So, for example, the system could learn based on previously observed errors and precursor messages to those errors. It could learn based on temporal and frequency domain patterns. It could sort of weekly fluctuations in order flow, weekly fluctuations in systems usage. It could learn by observing the system that is monitoring. It could learn the normal operating parameters of the system, and now if it sees something that falls outside those normal operating parameters, maybe a human operator should know. Now, if you could do something like this, now you can imagine an automated preemptive warning system, a system that could tell you, look, there is this thing that I just noticed, it is possibly indicative of a problem that you are going to encounter in a week's time, maybe you should do something about it. You can even think of a system that could take preventative actions automatically or remedial actions automatically. So, these are all in the realms of possibility once you have a system that is capable of learning how once you have a monitoring system that is capable of learning how a normal operating system looks like. Thank you very much, and I am open to questions. Yes.
Hi, thank you for your presentation. I think I have a very obvious question which you already got a lot of times after your presentations like this. How you deal with typical problem of all these approaches with abstract definitions in terms of performance of resulting system? I think it's a typical question after such presentation.
Yes. So, so when we started working on this was a question that we ourselves asked ourselves, like, why is it that everyone out there in the world is not building domain specific high level languages, because the potential benefit that you get out of it is huge. The thing that we realized was that we are working on in a very narrow specific domain. We are not building languages to handle general computation. We are building languages to handle what we already do, what we already know to do very well. So, in effect what we are doing is taking the manual effort that we do currently and building systems that can do that in an automatic fashion. So, at the end of the day, the code that we generate is fundamentally no different from the code that we MillenniumIT LSE write manually. So, in terms of performance, we do not actually expect loss of performance. Having said that, there is a flip side to the story, which is that you could potentially even expect to see improvements in performance, because if you take a complex system, have 100 engineers, 200 engineers building it, not every single one of them is the best you have. A lot of the code is going to be average. You go off and optimize in areas that are important. So, you will have sort of local pockets of highly optimal code and lots of sort of more average code around the system. When you are building a language that generates code, now we are dealing with sort of a leverage, a factor of leverage of 100 or 1,000, you can have your 10 best people building the tooling, which then means that the code that is generated out is as good as what those 10 people would have written if they wrote everything, which in sort of in the normal world is not possible. So, you can actually imagine a case where you can see improvements in performance. Now, again I will qualify that by saying this is only because we are dealing with a narrow domain. I do not believe it is possible to do this in general computation. Yes, please.
I want to ask about how much is the code generated from this software is the readiness for this code. Is it 100% ready for being used, or there would be additional?
Yes.
So again, I wanted to ask about how much the percentage for the readiness for this code generated from this tool, whether it's 100% ready or still need developers to continue the development for that application. Thank you.
So there are actually, I believe there are two different use cases. Now, the tool itself is capable of generating code that, well, generating, compiling code and giving a binary that you can just take and run. So the definition, so the language is capable of defining all aspects of a system. The compiler, the tooling can then take that specification and give you a binary that you can take and run. So it's completely ready. Take and run without any other human involvement. On the other hand, there is a second use case. Now, the code that is generated is fundamentally no different from code that would have been written by a human engineer. So, you could imagine a scenario where you say, okay, I do not actually want to use the tool to build my entire system. I want to use it to build this half of the system, right? And then I am going to use that as part of my engineering process, because the code that is generated is fundamentally no different from what a human would have written. You can have individual engineers, even in sort of teams or even individual engineers, use the tool to generate parts of the code that they have to build. So, there are two different use cases. Maybe we take it offline. Thank you very much.